Hey everyone, welcome back. So today we'll be discussing about the topic curse of dimensionality in machine learning. So what is mean by curse of dimensionality? Initially, let's talk about what is mean by dimensions. So what is mean by dimension? Okay, what is mean by dimension? Dimension is nothing but a feature. Okay, feature. Feature is nothing but a column. Okay, so we can tell that a dimension is nothing but a column. If a data is said to be three dimension, then it contains three columns. Okay, now you understood, right? What is mean by dimension? Okay, as the dimensionality increases, the number of columns increase. If we had a 28 into 28 dimensional data, it is said to be some around I guess it's around some something columns. It's around 600 to 744, I guess 744 columns, right? This is mean by dimension. So why the curse of dimensionality is introduced? So what is the curse? So here it indicates that when the data dimension, when the data's dimension is higher, there will be some problems. Okay, some curse will be there as the data set increases. As the dimensions of the data set increases, the curves will be there on the data. The first one is, as the dimensions increases, the data becomes sparse. Okay, the data becomes sparse. Okay, the data becomes sparse. Okay, because of this sparsity, finding patterns, okay, the finding patterns will become difficult. Finding patterns will become difficult because the sparsity, it introduces the difficulty to find the patterns, right? As the more and the more dimension, it becomes to find the pattern or to find the path for the optimal approach. Okay, so the next one is, as the dimensions increases, to find the patterns, as finding the patterns becomes difficult, then we require more and more training data to find the patterns. So this is the second curse: require more and more data. Require more training data. All right, more training data. The next case is, when the data finding the patterns is difficult, the model try to memorize the it try to memorize the data memorize the data. Okay, it memorize the data. Because of the, in training time, the accuracy in the training data set will be good. Okay, will be good, like it give better accuracy. But when it comes to testing data, which is which the model haven't seen yet, testing, it has been memorized the data. So because of this, this becomes bad. The accuracy becomes bad and bad. Okay, all right. So this is known as overfitting in machine learning terms. Overfitting, this is known as overfitting. Okay, so let me give you an example of in real life. As the dimension increases, we'll uh, we will find difficulty to find path. So example, okay. So let you are in a 1D plane. So here you are here. Okay, you are here. Your friend is here. So that finding him is very easy, because you need to look in only one line, right? Your friend is here, you need to look in only one line, so it becomes easier to you. You are at 0 and he's at x, you need to just find x values, that's it. Okay, when it comes to 2D plane, okay, when it comes to 2D, you are here, okay, and your friend is here. See, the variables have increased. Because of this, you need to find this entire area to find him. You need to search this entire area to find him. So it becomes more and more difficult. When we go to the 3D plane, okay, when we go to the 3D plane, we'll have three dimensions for it. If a data is here, it is represented as y comma x comma y comma z. Okay, now you understood, right? So you need to find him. You need to find this entire cube or cuboid. Okay, so this is the problem of higher dimensional data. Okay, so what are the algorithms? So what are the algorithms are mostly affected? So algorithms that are mostly affected are, so algorithms that are mostly affected are k nearest neighbors, KNN, because when the data is in higher dimensions, it need to find all the variables Euclidean distance, right? It need to find x Euclidean distance, y Euclidean distance, and z Euclidean distance. So more and the more parameters will be increasing as the dimensions increases. Okay, similarly SVM and decision trees, okay, clustering, it becomes more and more difficult. Okay, how we can handle it? Handling techniques. Okay, so we can handle it. Okay, so we can, there are three ways. Okay, the first way is feature selection. Feature selection. Okay, so you have 100 features. 100 features. Using feature selection, you will only take 20 features. You will only take 20 features. Okay, so let's take an example. So we have discussed that to find the height using weight. So height, name, father height, okay, and weight. Okay, so height is directly proportional to weight, right? The father height is directly proportional to the candidate height, right? His father's height is proportional to his candidate in most of the cases. In hypothetical way, let's assume that. So here the name does not have any effect on weight, right? So it does not have any effect on weight, so we can remove the name. So we can remove the name. So we will choosing only two features out of three. So three dimension is converted to two dimension. This is known as feature selection. Okay, and the problem is when we have, so this is the basic example. Let's say there are many, let you have to convert 100 dimensions to 20 dimensions. The entire 80 features will lose the data, right? The 80 features data is not used. It might be a problem, right? It will make a problem while we are calculating the accuracy, because we have missed around 80 features. 80 features are missed. Okay, so to eliminate this, we have come up with the second solution. The second solution, that is feature extraction. Feature extraction. So what is mean by feature extraction? So similarly, the 100 dimensional data will be converted into 20 dimensional data, but here the entire 80 dimensions are not left behind. The entire 80 dimensional the data will be compressed into 20 dimensional data. The entire 100 dimensions will be compressed into 20 dimensions without any data loss. This is known as feature extraction. So the algorithms we use is PCA. Okay, PCA. This is principal component unit. Principal component analysis. Component analysis. Okay, component analysis. So using this, we will extract the features without compromising the data, the patterns in the remaining features. This is the second approach. The third approach is using the tree ensembles, tree tree ensembles, tree ensemble algorithms, like using the random forest algorithm, or using ensemble techniques, ensemble technique for with numerous amount of DTs, like direct decision trees, sorry, more and more amount of decision trees. Using this, we can reduce the, like, these algorithms will not be much affected by the curse of dimensionality. Okay, all right. So this is the theory part of the curse of dimensionality. Okay, so what is mean by dimension? It is mean by feature. It is mean by feature, and feature is nothing but a column, right? So the curse means the more the dimensions, the more the problems will occur. The more difficult will it will be more difficult to find the patterns. Okay, so because of this, it memorizes the data. So it performs good in training data, but does not perform well in testing data. This is known as overfitting. The most of the algorithms that are affected are KNN, decision tree, SVM, and clustering techniques. Okay, and how we can handle it? So there are three ways. The first way is feature selection, and second way is feature extraction, and third way is using tree ensembles. Okay, tree ensemble algorithm techniques. So this is the curse of dimensionality.